Hi everyone, this is lecture 11 of engineering mathematics from the University of Notre Dame. So today we will continue discussing about the four fundamental subspaces of a matrix A, and we're going to start with one application on graphs just to demonstrate how the different subspaces look for particular matrices with some structure. And then we will move on to expand on our understanding of these fundamental subspaces, talking about concepts of orthogonality. So let's move on. So most of the material is from chapter 3 and chapter 4, section 4.1 of Strang's Introduction to Linear Algebra textbook that we use for reference in all of these lectures. All right, so let's look at an application to graphs and networks. I'm going to be referring a lot to circuits, but you can use analogs of things that we will discuss today to other applications such as structural components, hydraulics, interconnected complex systems, or anything else that you have in mind. So let's consider that we have a circuit that has 4 nodes, and we call the potential at these nodes as x1, x2, x3, and x4, just in some arbitrary fashion. And then, as you see here, I'm indicating also the currents that these potentials induce in the edges of these graphs. So this is current y1, y2, y3, y4, and y5. The direction of positive currents is a little bit arbitrary, but somehow you will see when I write down matrix A, we follow one of the possible conventions in the way we indicate the currents. So let me start with defining the matrix A. So the matrix A, as you can see from the equation to the right, it's basically a difference matrix. What it does is it takes differences between potentials. So you can see the first row is x2 minus x1, second x3 minus x1, x3 minus x2, etc. So effectively, the difference matrix, what it does is it computes the differences in the potentials. And you recall from your undergraduate courses, difference in potentials basically have to do with currents. So somehow the effect of A on the potentials X will be related eventually through Ohm's law to the currents Y1, Y2, Y3, Y4, and Y5. And you can see actually our convention now for the currents. Here we have the difference x2 minus x1. So we put the current to be positive towards node 2. Similarly here we have x3 minus x1, x3 minus x1. So we put the current to be positive towards x3. So in some domains, this difference matrix A is also called the incidence matrix, but I prefer to call it the difference matrix as we introduce it in some examples we did in, if I recall, lecture 1 or lecture 2 earlier in the course. All right, so that's our matrix A, and I'm going to write it explicitly to indicate that the columns of the matrix A are referring to the different nodes. So we have 4 columns for each of the nodes, and then we have 5 edges, each corresponding to 1 row in the matrix. We have 5 currents and we have 4 potentials. So that's our matrix A. All right. So since we talk about fundamental subspaces and we want to use this as a typical example, the first question is, what is the null space of A? So can we get non-zero potentials X so that AX equal to 0? And you can see from our difference matrix that actually, if you try to solve Ax equal to 0, the first equation will give you x2 equal to x1, the second x3 equal to x1, the third x3 equal to x2. Basically, the null space consists of all vectors that they are parallel to the vector 1, 1, 1, and 1. So the null space is a line, has dimensionality 1, and basically this is as much as, based on what we know up to now, we can say about the null space of this matrix. So this is the basis element of the null space. So since n in this matrix is equal to 4, n minus r, 4 minus 3, I'm sorry, so the null space we said has dimensionality 1, so n minus r is equal to 1, so r has to be equal to 3, so the rank of this matrix is obviously 3. So effectively we anticipate to get 3 pivots and 3 independent columns and 3 independent rows, and we will visit this information for the column and row space shortly. The null space, of course, is a subspace of R4 of dimensionality 1. So let's look at the column space, and we already said that because the null space has dimensionality 1, the column space needs to have 3 independent columns, basically. So the R is equal to 3, and the way to identify which of the 4 columns are independent is by producing the reduced row echelon form for the matrix A. And I'm giving you this form here. You can do your elimination process, and you can see immediately that the 3 first columns are the 3 pivot columns. So effectively, the first 3 columns of A form a basis for the column space of A. So this is the basis. These are the 3 basis elements for the column of A. And I remind you, I take the opportunity to remind you once more that the matrix R identifies which columns to include in the basis, but you need to use the columns of A, not the columns of R for that basis, because the row operations have changed the column space, contrary to what we have said about the row space that remains unchanged. So the column space again are consists of the basis consists of the first 3 columns of the matrix A. All right. So the column space has dimensionality R equal to 3. The null space has dimensionality equal to 1. So let's look at the row space and try to identify which rows of this matrix A form the independent rows and the basis for the row space. Now, you may say, without thinking much, that maybe the first 3 rows are form the basis for the matrices A and R. But if you look carefully, row 3 of A, it's really row 2 minus row 1. All right, so row 3 is a dependent row, which means when I do row elimination, most probably with row exchanges, row 3 has been moved to the bottom. It's one of these 0 rows. So effectively, it comes out that in this particular problem, the independent rows are rows 1, 2, and 4, not rows 1, 2, and 3. There is a very nice way to identify without doing any algebra, which rows correspond to, they are independent. And so let me remember each row corresponds to a current. So if you look at the first, second, and third row, and you look at the currents, they are in a loop. So we can immediately affiliate dependent rows with loops. And let's look at rows 1, 2, and 4. If you look at the currents 1, 2, and 4, they form a tree. So you can affiliate independent rows with trees in the graph. So we can actually immediately put a statement down and say that if these rows form a loop, they are dependent. If they form a tree, basically they're independent. And you can think of rows again as corresponding to the currents as you see on the graph that I saw on the right. So the left null space, of course, would be our last space that we need to be able to say something about. So, of course, the row space, let me just go back on this. You remember for this problem, R is equal to 3, so the row space has dimensionality 3, and you can take as its basis, actually, these first 3 rows of R, or you can take the first, the second, and fourth row of A. Remember, row operations leave the row spaces of A and R identical, so in this case, it's easier to take directly the rows of R, but remember the third row came through row exchange when it comes to the matrix A. All right, so back to the left null space. So we need to find the y vectors so that A transpose equal to y. So the left null space, you remember, equivalently, we can write it as y transpose A equal to 0. So effectively, we're looking for the dependencies between the rows. And we already have said that row 3 is row 2 minus row 1. So if the y vector captures the dependencies between the rows, this equation immediately can be transformed to a basis vector. And you can see here row 3, 1. Minus row 2, so minus 1, plus row 1, 1. So one solution to the left null space problem is 1 minus 1, 1, 0, 0. Actually, if I can go back here, if you remember the dependencies between rows, we said an easy way to say something about it is if the currents form a loop, then the corresponding rows or currents, they depend. So you can actually see this basis vector corresponds to the loop y1, y3, y2. And actually, if you follow the direction of the currents, you have plus y1, plus y3, and then y2, if you go in the loop around, is minus 1. Now, in that fashion, actually, so we don't have to do any algebra, you can identify a second loop that involves y3, y5, y4, and you can see the signs here will be 1 for y3, 1 for y5, and minus for y4. And you can actually check that this is indeed a solution to the left null space problem, and this is the dependencies between the rows that we identified earlier. So the left null space, you remember M is equal to 5, R is equal to 3, so M minus R is 2, so it's not surprising that we already have computed the two basis vectors of the left null space. Okay. So there is actually a remarkable result that it comes from linear algebra, but is fundamental result in connected graphs. And this result that goes with the name of Euler's formula, it says that the number of loops in a connected graph is the number of edges minus the number of nodes minus 1. And you can test this formula in our example. The number of loops is 2. And here we're referring, by the way, to independent loops. So, you can think of the big loop going all around is the sum of the two smaller loops, so we don't count it. So we have two independent loops, y1, y2, y3, and y3, y5, y4. So we have two loops plus nodes minus 1. We have 4 the number of nodes in this case is 4. So plus the number of nodes, right? So number of loops plus the number of nodes minus the number of edges. We have 5 edges. So this is 4 minus 5 minus 1 plus 2 equal to 1. And it comes to be equal to 1 that you see here on this Euler formula. Okay. And so this is a fundamental equation that relates nodes, loops, and edges in connected graphs. And why is this related at all to our linear algebra conversation? Well, remember that the dimensionality of the left null space is M minus R. And in our problem, what is R? R is N minus 1. So this equation is actually that you see here is literally Euler's formula. What is M minus R? Is how many dependent rows I have, which we identify with the number of loops. This is the nodes minus 1. And what is M? By definition, when we set the difference matrix A, is basically nothing else but the number of edges in the graph. So linear algebra somehow, it's very natural in understanding graphs, and you can see a trivial example by relating the dimensionality of the subspaces of the matrix A with Euler's formula. All right, so let's go back to the left null space and try to see what exactly is going on. So remember the the left null space. We have identified 3 pivot columns. 1, 2, and 4. So it has dimensionality M minus R, which is 2, and we related loops with dependencies in the rows. But what I want to do is I want to affiliate now the left null space for this circuit problem with a little bit physics. All right, so we need to bring some physics and see that linear algebra actually is capable of capturing some fundamental laws in physics. So let's see what those laws are going to be. So what I'm going to do is I'm going to the left null space problem, you remember, is A transpose Y equal to 0, right? A transpose Y equal to 0. So what I would like you to think is, take this equation, A transpose Y equal to 0, and write it down explicitly by row to 4 equations. So let's look at the first equation. It says minus y1 minus y2 equal to 0, or if you like, y1 plus y2 equal to 0. So effectively what it tells you is that the currents, the net currents in and out of node 1 are equal to 0. Similarly, if you look at the second equation, what you have is y1 minus y3, y1 minus y3 minus y4 equal to 0. And again, it tells you basically that the current in node 2 is equal to the currents out at node 2. So effectively what we're stating here is nothing else but what is called as the Kirchhoff's law. The Kirchhoff's law basically is nothing else but a balance equation for each node that tells you that the net current in each node is equal to 0. So you can think of this as a conservation equation that relates the currents in the graph. So I'm going to use this equation to write down some fundamental equations that govern the potentials with the currents by using also Ohm's law that we're going to see in a follow-up slide. All right, so let's see how the whole thing is going to work. We started with the potentials x we define the potential differences that I call them here E. So A times X gives me potential differences. And Ohm's law, basically, through a material property that we call here the conductance of the edges, defines the currents as a function of the potential differences. Okay? So if you know the potential differences, Ohm's law will tell you what the currents are. And the Ohm's law takes the form Y equal C times C. This is what we will call in a problem in physics a constitutive equation that relates one state variable, here the potentials, with another, here the currents. Okay, Y is equal to C times C. All right, Kirchhoff's second law, we just said it, identifies that A transpose Y equal to 0. And we already gave a physical interpretation of this. I'm not going to repeat it. So what we have is we are actually having three equations. This is Kirchhoff's current law. It's a balance equation. Ohm's law, it's a constitutive equation. And this matrix A introduces a structure somehow that allows to identify that the potential differences is the quantity that I need to define my currents. Okay, so let me put all of these things together. All right, so actually these slides we have been a little bit earlier, so let me just bypass. We already talked about the Kirchhoff's current law, so we don't need this. So what I'm going to do is I'm going to go back to my three fundamental equations, and before I actually do this, so we can finish this application with this slide, let me just generalize a little bit the Kirchhoff's law. So remember, the Kirchhoff's law for the currents basically says the net current in every node is equal to 0. So what we're going to do is, rather than taking it equal to 0, we're going to assume it that is equal to F, where you can think of F as being an external source of currents in each node. I mean, if this was a structural problem, right, and it's, the edges were trusses or beams, you can think that F corresponds to the external forces in every node. So the equation A transpose Y equal to F for a structural problem will imply basically that balance of the internal and external forces at that node. So in our case, the currents, the net currents in and out have to be balanced by the source, the external source that is given by F. So by generalizing this, we will be able to see sort of a more useful form of this governing equation for this problem. So let me go back. We have three equations. Remember, one defines the differences between potentials. The constitutive equation that from the potential differences gives me the currents, and then Kirchhoff's generalized form that tells me A transpose Y equal to F. So what we will do is take Y, plug it in there. So we're going to have A transpose C E, and E is A X. And here is the final answer. We basically see that to be able to identify the potentials in this problem, we need to solve an equation A transpose C A X equal to F. This equation is extremely fundamental to linear algebra. It's going to come up all the time, and as a matter of fact, in case you forget, just take the matrix C temporarily to be an identity matrix, and you can immediately see the matrix A transpose A showing up here, and A transpose A will be our fundamental matrix when we discuss about least squares methods. Okay, so it's just amazing that somehow the structure of the graphs has been able, with simple equations, to identify this general form that, as I said, is fundamental to many problems in engineering and the sciences. All right, so I think we're done with an application of the four fundamental spaces to to graphs. So let's move on. And I want, as a sort of a mini appendix, to bring something that will be useful in many aspects later on in the course. And I want to remind you what rank 1 matrices are about. And then I want to show you that I can take any matrix of rank R and write it as the sum of R matrices of rank 1. We have mentioned this thing earlier in a previous lecture, and so we will see it now explicitly since we have a better understanding of the rank of a matrix. So we will see this clearly in this lecture as well. So let me take this matrix that you see here, and this matrix is rank 1, and you can actually see all the columns are multiples of the column 1AB, and you can see all the rows are multiples of the row 2, 3, 7, and 8. So this matrix actually can be written as this outer product, if you like, of the column vector 1AB and the row vector 2, 3, 7, and 8. Remember, an inner product, you get a scalar. Here, when you multiply a column a vector with a row vector, you're actually getting a matrix, in this case, a matrix that is 3 by 4. So every column is proportional to this column, and every row is proportional to this row. So there is only one independent column, which is 1AB, this vector U, and there is only one independent row, which is this vector V. So U and V is what you need to generate this matrix A. And obviously, this matrix having only one independent row and one independent column has rank 1. So never forget that all rank 1 matrices have basically the form UV transpose, where U is the basis of the column space and V is the basis of the row space. All right, so what I'm going to do is now I'm going to bring up a matrix that has rank 2 and show you that somehow we can write that matrix as the sum of two rank 1 matrices. So let me try to do this. So let me start with this matrix that you see here on the left. Okay, 1, 1, 4, 0, 1, 2, 3, 7, 20. If you do elimination on this matrix, you're going to come up with a 0 row, which means one of the rows is a linear combination. The third row, a linear combination of the other two rows. You can also see that the pivot columns is column 1 and 2. Okay, so in principle, the way we get to this matrix R, to the row reduced echelon form, is we multiply A on the left with some elimination matrices, and E times A gives us R. So let me take this elimination matrices that altogether I call them E, and define the inverse matrix E minus 1. And so I denote this matrix here as C. So obviously, if EA is equal to R, A is equal to C times R, and the C matrix here is given by what you see in the equation, is the matrix 1, 1, 4, 0, 1, 2, 0, 0, 1. And just as a reminder, to come up with this inverse of the elimination matrix is really you basically start with the identity matrix, and below the pivot elements that are 1 here, you have to put the multipliers that you use in the elimination process. And obviously, these multipliers come to be 1, 4, and 2 in this problem. And if you don't believe me, you can actually do the elimination to get this, identify what the multipliers are, and you can see immediately that you're getting this nice matrix C here. Now, why am I telling you all these things, right? So let me. So we said that this matrix A has rank 2 because we only have 2 pivots. Okay, so we want to see if there is any structure in this rank 2 matrix. So let me do a few observations first. Observe that the first column of A and the second column of A, which are basically the 2 independent columns, are the same as the first column and the second column of this matrix C. And you may say, is that a coincidence? Why is that the case? No, it's not a coincidence. I mean, this is a general result. Notice if you take here, we have identified our 2 by 2 identity matrix, right, as part of the elimination process. So if you multiply the C matrix by the first column, obviously you get the first column of the product has to be the first column of the matrix A. So it's 1, 1, 4, because this one here. Similarly, if you take this C matrix and you multiply by 0, 1, 0, you get the second column of A, which is 0, 1, 2. So it makes sense, because this is 0, 1, 0, that this is also the second column of matrix A. So effectively, if I call this column U1 and the second column of A U2, in the C matrix I have U1 and U2, and I'm going to go a little bit further and call the first row of the row reduced matrix V1 and the second row V2. And remember, those 2 rows form the basis of the row space, basically of R, and of the row space of the matrix A. So what I have is, if I can go to the next slide, what I have is, I have, let me see if this equation I need is here. I don't see it yet, so give me 1 second. Here it is. So if you look at this nice matrix, we have the A matrix equal this product of C and R, and we said that the first 2 columns of C are the columns U1, U2 of the matrix A. And let's call this third column, whatever it is, U3, okay? But certainly we said that U1 and U2 are the first 2 columns of A because of this identity matrix. And then this is row 1 that I call V1 transpose, and this is row 2, which is V2 transpose. And on the bottom I have a 0 row, okay? So effectively, if you do the multiplication of C times R, what you get is, you get U1 V1 transpose, that's a matrix, row 1 matrix, U2 V2 transpose, that's rank 1 matrix, and then U3 times the 0 row gives you 0. So basically, we have managed to write down a rank 2 matrix as the product of, as the sum of 2 row 1, I'm sorry, 2 rank 1 matrices. And these rank 1 matrices, each of them is formed with the columns of U1 and U2. These are the pivot columns, the independent columns of the matrix A, and V1 and V2 are the independent rows of R. This is an amazing result, right? So we basically have been able to write down a rank 2 matrix as the sum of 2 rank 1 matrices, where these rank 1 matrices have been identified as via the independent columns of A, and the independent rows of R, which are the same as the independent rows of A, but here I'm using, in the derivation, I'm using the independent rows of R. So this result that we derive for a matrix that has rank equal to 2 can obviously be generalized to any matrix of rank R, and we can state with confidence that every matrix that has rank R is nothing else but the sum of R rank 1 matrices. Again, this is an amazing result, and maybe I hope you can appreciate the significance of rank 1 matrices. So lots of algorithms use this type of decomposition of a general matrix with rank R to the sum of R matrices of rank 1. So remember this, because we will get multiple ideas later on in linear algebra that use this either as exact expressions as we have, as you see here, or as approximate expressions in some other different scenarios. This expression, the way we have it here, is again is exact, right? So the statement that you see in this slide is an exact statement. Okay, so we discussed the 4 fundamental subspaces. So let me just summarize all of them. We produce this row-reduced echelon matrix R. We identify the R pivot columns, and we said the R pivot rows of R will basically form the basis of the row space of R and of A. They both have the same, the row space doesn't change when we do operations. So usually we take the pivot rows of R as the basis of the row space of A. We said when it comes to column space, identify the pivot columns in R, but take as a basis of the column space of A the corresponding columns of A. Not of R, because they don't have the same column space. We identify the null space solutions. So N minus R are the spatial solutions. We have discussed in earlier lecture how to compute those. And eventually we have defined the left null space, all right? And the dimensionality of the left null space is M minus R. These are the 0 rows basically that we get when we do elimination, and the left null space tells us the combination of the rows that gives us 0. And somehow we managed to bring some physics in, and see that this left null space was very much related with a balance equation, in this particular case with Kirchhoff's current law, stating that the net currents in a node in a circuit are basically equal to 0. All right, so we're now ready to move to ideas of orthogonality, and what I'm going to do is I am going to discuss something we already have seen, so I'm going to try to go very fast because it's all just a review. So I would like to discuss a little bit about inner product spaces. So we're going to bring the concept of inner products in vector spaces, and we're going to go from just a regular vector space to what we call an inner product vector space. So let's take this is the main fundamental slide that I want you to know. You take a vector space, and in addition to all the operations that we know in a vector space that include additions of vectors, multiplications with constants or linear combinations of vectors, we also define what we call an inner product between two elements of that vector space U and V. And this inner product is a scalar that obeys these properties that you see here, 1 to 5. So let me fast go through all of them. They are all of them very familiar to you. One is this commutative property that says that the inner product is symmetric, so you can take the inner product of U and V, and that is the same as the inner product of V and U. You have a distributive property. If you want to take the inner product of U with V plus W, this is the same as the inner product of U and V plus the inner product of U and W. If you try to identify the inner product of a multiple of U with a vector V, this is the same as that constant times the inner product of U and V. So this is an associative property with respect to scalar multiplication. And then if the two vectors are the same, you have two fundamental properties that we already have discussed because they are related with the length, the definition of the length of vectors in a vector space. So the inner product of a vector with itself is always greater or equal to 0. And if that inner product comes to be 0, the only way for that to happen is if the vector v is equal to 0. Now, in a given vector space, there's many different ways of defining this inner product. And, as the more courses you take in mathematics, the more interesting vector spaces you will meet. But really, we are going to use our familiar inner product in the space, let's say Rn or Rm, that we have seen in an earlier lecture, okay, where effectively the inner product of u and v is u1 v1 plus u2 v2 plus un vn for the space Rn. A lot of times, a vector space, is the collection of vectors, and the only thing we have defined is basically this addition of vectors and multiplication with scalars. This inner product vector space is basically the same vector space with all the properties we have seen, but in addition now we introduce an inner product. So an inner product, has this extra machinery that brings this concept of an inner product with the properties that we have seen in the earlier slide. Okay, so this is what I mentioned before. If you have two vectors in Rn, the inner product basically is given by this nice formula. And practically in every application that we will see in this course, this is the inner product that I'm going to use when it comes to vectors. I have a few examples, and I am not going to discuss them on this presentation, but let me just define what is on each slide, and then you can go and read and practice the rest. So as I said, you can find different types of inner products that all satisfy the required properties, and so they're acceptable inner product definition. So if I have two vectors in R2, out of craziness, I can define an inner product that rather than being u1 v1 plus u2 v2, I say u1 v1 plus 2 times u2 v2. So if you actually follow all the properties that I had listed for the definition of the inner product, you can actually see that this satisfies the inner product definition, and it's an acceptable inner product. Okay, so you can actually follow this as an exercise in your spare time. This is the remaining of the properties exactly for this particular inner product. And in general, actually, you can generalize the familiar inner product to a form like this, but all of these coefficients C have to be greater than 0. So you may want to actually show that if you have an inner product defined like that, that really you need this C greater than 0, okay? So I'm gonna leave it up to you to actually go and see where is that definition, C greater than 0 coming from, okay? So, all right, so let me define another weird inner product between two vectors in R cube. Notice here there's a minus sign that may be troubling, and here it is actually, you can, if you take this particular vector in R3, and you take the inner product with itself, and you follow this given formula, you see that the inner product with itself comes to be a negative number, and that's a no-go. It's like saying the magnitude of this vector, the magnitude of this vector, we have not defined it yet, but we refer to it in lecture 1 or 2 as being the square root of this inner product. Obviously, if this number is negative, we're in trouble, so this is not a valid inner product. You can actually prove using the 5 properties of the inner product additional properties, that dot product of any vector with a 0 vector gives you 0. you can actually reverse the summation that we had in one of our properties, and so that U plus V inner product with W is the sum of these two inner products. And also you can prove property 3, where now the constant is not on the U vector but on the V vector, and you get basically the same formula as before, C times the inner product of U and V. The proofs of all of this using our fundamental axioms from a few slides ago is given on this slide, so you can again use this as an exercise. The idea here is, in mathematics, you introduce some fundamental axioms. You say, this is how I define it, and then anything else should flow out of those axioms. So these rather trivial properties that you see here, they are not assumed in the definition of the inner product. They are derived from the fundamental axioms. All right. The definition of the length, I already mentioned it. Okay. You can similarly define the definition of the distance between two vectors as the square root of the inner product between U minus V and U minus V. And again, there are multiple ways to define distances between vectors, but once you have an inner product, there is a natural way to define distances using square roots of inner products. The last equation I had given to you before, and actually I prove it, and so I'm not going to do this again. The inner product between two vectors U and V is the magnitudes of U and V times the cosine between the angles of these two vectors. And using this formula, we actually have already introduced the concept of orthogonality between two vectors. Two vectors U and V are orthogonal if the inner product is 0. Okay, so lots of these things are what you will expect based on things you know from earlier classes in linear algebra or geometry. A reminder of a unit vector. A unit vector has magnitude 1, so if a vector is not unit and you want to normalize it, you have nothing to do but basically divide by the magnitude of V, which is again the square root of the dot product of V with itself. So this definition of inner products between vectors, you can actually extend it to things that you don't necessarily affiliate with vectors, right? But you can generalize the concept of a vector space. So if you think of the space of polynomials of nth order, you can define an inner product in that space of polynomials by using the coefficients and following similar definition to the inner product in Rn, all right? And by taking the summation of the products between the coefficients A0, B0, A1, B1, etc. And this is, not a useless exercise, because in essence, if you have two polynomials, it would be of interest somehow to be able to define, let's say, a distance between the polynomials. So if you try to approximate them, one polynomial with another, how far apart are they? And this concept of the inner product that you see on the slide is a very good way to define a measure of the distance between polynomials. And similarly, you can define the magnitude of a polynomial and many other things you'll be interested. So again, we're pushing the envelope here by showing you that when we talk about vector spaces, every element in that space can be a matrix, right? And we already have seen it, and you may actually wonder what is the inner product between matrices. So I'm going to leave you to think about it, all right? Just always remember, you need to satisfy the fundamental axioms for the inner product that we have seen before, but the definition of the inner product is not unique. So you may come up with your own inner product and name it after yourselves. Okay. These properties of the norm or the magnitude of a vector, basically all of them are derived from the properties of the inner product. So the magnitude is always greater than 0. It's only 0 when the vector is 0. And if you calculate the magnitude of a vector times a constant, is the absolute value of that constant times the magnitude of u. You may wonder where did the absolute value came. Remember that this magnitude of c times u is the inner product, is the square root of the inner product of cu with itself. So from that inner product, you're going to get the square root of c squared, and that's how you get the absolute value of c. And you have similar properties with distances between vectors. They're always greater or equal to 0. The distance is equal to 0 only when u is equal to v. And the distance here, following our definition, is symmetric. Okay. There are actually some applications beyond linear algebra, for example, in probability theory, where you define distances that are not symmetric, okay? But the type of things we play in this course, the distances are symmetric. A reminder of the Cauchy-Schwarz inequality, very, very important. You remember the inner product is equal to the magnitude of u, the magnitude of v, and the cosine of the angle. So because the cosine of the angle in absolute value is less or equal to 1, that gives you the Cauchy-Schwarz inequality, and from which you can immediately show the triangular inequality, right? You can actually take the squares on both sides because they're positive, and you will get here 2 times the inner product of u and v, and you can actually show that in absolute value this is less than 2 times the magnitude of u and v, and you can show the validity of this triangular inequality. We already defined what orthogonality between 2 vectors means, right? So the inner product of u and v is equal to 0. So you can show that for 2 vectors u and v that are orthogonal, you have the Pythagorean theorem. And again, expand this, use the definition of this norm as the inner product of u plus v with u plus v, expand it, and you will get this plus 2 times the inner product of u and v, which is 0. So you get the Pythagorean theorem when u and v are orthogonal. All right. So we are in the last stretch of this very long lecture. So we're going to discuss about orthogonality of the fundamental subspaces of a matrix A. So we're starting with reminder again that 2 vectors are orthogonal when the inner product, written here, sort of in a matrix notation, V transpose W is equal to 0. And we already said that the Pythagorean theorem is applicable in these cases. So now what I want to do is I want to expand this definition of inner product to subspaces and define the following concept. I'm going to call that 2 subspaces are orthogonal when V transpose W equal to 0 for any vector little v coming from the subspace capital V and any vector W coming from the subspace capital W. So effectively, I'm going to call 2 subspaces orthogonal if I take any arbitrary elements from the 2 subspaces, and if I take their inner product, if it comes to be 0, then I call these subspaces orthogonal. So the key buzzword here is for every V and for every W, not for some V and some W, for every V and every W. So this is what I call orthogonal subspaces. So let me give you a summary of what the remaining of this lecture is going to be. We're going to prove something extremely fundamental to linear algebra. We're going to show that the row space of a matrix is orthogonal to the null space of that matrix. All right. So we already have we know that both spaces are subspaces of Rn. Now we're going to prove that they are orthogonal to each other. Even further, we're going to prove that the, where is it? We're going to prove, so let me just go back. We're going to prove that the column space of A is orthogonal to the left null space. Okay, so so we have the null space and the row space being orthogonal, and then we have the column space and the left null space being orthogonal. Not only we're going to prove that these two pairs of subspaces of Rn and Rm are orthogonal, but we're actually going to prove that they are what we call orthogonal complements, that their dimensionalities actually match. So together, the null space of dimensionality n minus r and the row space of dimensionality r, they make the whole of Rn. And similarly, the left null space of dimensionality m minus r and the column space of dimensionality r, they make the whole of Rm. So this is what we call orthogonal complements. So you can think if the row space and the null space are orthogonal complements, every vector in Rn can actually be split in two vectors, one that lives in the row space and one that lives in the null space. This is in general. So if you take an arbitrary x in Rn, you're going to write it as you can write it as a component that's in the row space and a component that is in the null space. That's what having these two spaces being orthogonal complement means, and we will elaborate as we move on in this lecture. So obviously, we're going to be using a lot the concept of the dimensionality that we have seen before. So the dimensionality uniquely identifies a subspace. So if a subspace has dimensionality D, every basis for that subspace contains D independent vectors. And if somebody gives you D independent vectors that span a space, then if somebody gives you D vectors that span that space, then these vectors need to be independent. Okay, where D here again is the dimensionality of that space S. All right. There's nothing on this slide. It again talks about the Pythagorean theorem, so I am going to bypass it. So two vectors are orthogonal. This is our definition. And there is an example here on this slide of, let me actually do this because you may have to do some homeworks like this later in your homework. So if I give you a vector u and I tell you to find me a vector v that is orthogonal to the vector 4 and 2, so effectively what you need to do is you need to set the inner product equal to 0. So if you take v2 to be equal to 1, you immediately see that v1 is minus 1/2. So basically, the space of vectors that is orthogonal to the vector u is all the vectors that are parallel to the vector minus 1/2 and 1 that you see here. Okay, we will need to do calculations where we will need to identify, given a subspace, we will need to identify the orthogonal subspaces to that space. So here you see a trivial calculation where I give you a line, which is obviously a one-dimensional subspace in R2, and I'm asking you to identify the subspace that is orthogonal to U, and that comes to also be a line. So interestingly, note that the dimensionality of this orthogonal space is 1, and the dimensionality of this line of the vector u4, 2 is also a line of dimension 1. And interestingly, 1 plus 1 is equal to 2. Okay, so if you want to start thinking what this thing implies, 1 plus 1, the two things together, they make the whole of R2. Again, I'm not going to bother about the Cauchy-Schwarz inequality. We already have seen it, so you can, this is what I mentioned before. So, and graphically, the Pythagorean theorem, you can see on the right two vectors meeting at 90 degrees, and you can see that the magnitude of u plus v square is the magnitude of u square plus the magnitude of v square. So what I'm going to use from now on, I'm going to operate on Rn and Rm to prove the fundamental equations that I mentioned about the orthogonality of the fundamental subspaces. And I'm going to use the inner product that is our regular familiar inner product, U1 plus V1, U2 plus V2, etc. So this is the inner product we will use in the rest of the lecture. All right, so let's go to the heart of this lecture, talking about the orthogonality of the four subspaces. So you remember this nice schematic from Professor Strang's book that I showed you before. We will elaborate significantly in this course. We had in the part one of the fundamental theorem of linear algebra, we identified the dimensionality of each of the fundamental subspaces of A. So, for example, we said that the null space has dimensionality n minus r. The column space has, the row space has dimensionality r. But from that schematic, you notice the way it is drawn, these two fundamental subspaces of Rn, they are shown to be meeting at 90 degrees. And the idea here is we will prove that they are orthogonal to each other. Okay, and orthogonal means if I take any vector in the null space, I'm going to show that it's orthogonal to all rows. And if I take any vector that's a combination of the rows, then I'm going to show that is orthogonal to the null space. Don't forget that the two subspaces here, if they come to be orthogonal, as we will prove, they only meet at the zero vector. Okay, this is extremely important. They only meet at the zero vector. The zero vector needs to be part of both subspaces, otherwise the null space and the row space don't qualify to be called subspaces of Rn. And we will show similar things about the column vector and the left null space. They're orthogonal to each other, as you can see graphically here, and they share again the 0 point. So so we will see that this schematic contains actually practically everything you need to know about linear algebra. So I'm going to bypass the statement on the bottom of the slide, as we will see this concept elaborated when we discuss about least squares methods. So I don't want at this point to confuse you. So so we already discussed that the row and column spaces have dimensionality R. Okay, we discussed about the two null spaces to have dimensionality n minus r and n minus r. So the dimensionalities seem together. If you take the null space, the row space, they give you n. So they seem to match the dimensionality of the space from to which they belong, but there is nothing about orthogonality or anything like that yet. So what we need to do is we need to prove this statement that I gave you, that the row space and the null space are orthogonal subspaces within Rn. Okay, so both the row space and the null space are subspaces of Rn, and we need to prove that they are orthogonal. So we need to prove that a vector from the null space is literally orthogonal to every row of the matrix A, because if it is orthogonal to every row, then it's orthogonal to the combination of the rows, which means it's orthogonal to any element of the row space of the matrix A. The proof actually is given on the next slide, but before I move to the proof, let me remind you our definition. Two subspaces, capital V and capital W, are orthogonal if for every little v in capital V and every little w in capital W, these two vectors are orthogonal to each other. Okay, their inner product is 0. All right, so let's prove that the row space and the null space are orthogonal. And I realize there is, after a long lecture, I keep forgetting what slides are coming next. So I need to sort of elaborate a little bit before we discuss this orthogonality. I need to elaborate a little bit on the definition of the orthogonality of subspaces, because it is possible that what you consider geometrically to be orthogonal to each other, those two things, they are not orthogonal subspaces. So let me just give you an example, and I apologize for leaving this for 2 slides down the road, but let me give you an example where I'm going to challenge this orthogonality understanding that you may have for 2 subspaces. So let's do the following thing. Think that you have 2 planes in R cube in 3 dimensions that they meet at 90 degrees, all right? So you can think 2 of the walls in the classroom, or 2 planes, meeting at 90 degrees to each other. So somebody will say, wait a second, this plane V is obviously a 2-dimensional subspace of R cube. W is a 2-dimensional subspace of R cube. So then these 2 subspaces have to be orthogonal. Well, they are not orthogonal. And they are not orthogonal because the definition of orthogonality says for any vectors V and W, the inner product has to be 0. So if I take a vector V on this line that you see here, belonging to the capital V space, and I take a vector little w to this, from this space W being on this line, the inner product in V and W is not 0, right? I mean, the V and W, you can make them to be the same vector, and that inner product is greater than or equal to 0. I mean, if you take a non-zero vector V, it would be greater than 0. So the idea here is these 2 spaces V and W cannot be orthogonal subspaces of R cube. All right, so that's a common misunderstanding you may have with orthogonality of subspaces. Let me give you something that, again, I mentioned before, and you may want to start thinking about it. We said that this space, subspace V, is of dimensionality 2. We said that this space W is of dimensionality 2. So V and W together, if you add them, you get dimensionality 4, and that's no good, because if they were really orthogonal complements actually of each other, they should make the whole of R cube, but we have an issue here because 2 plus 2 is greater than 3. Okay, bottom line, V and W are not orthogonal to each other. Here is an example of 2 subspaces that are orthogonal to each other. Take a plane passing through the origin 0. So this is a subspace of R cube. And then take a line orthogonal to that plane, passing from the origin 0. Or, take actually any, well, in this case, because I talk about orthogonality, I'm going to take a line that's orthogonal to V. So the line is a subspace of dimensionality 1. The planes of dimensionality 2, so 2 plus 1 equals 3. That's nice. And immediately you can see if you take any vector in W, okay, it is orthogonal to any vector in the space V. Okay. All right. So again, try to remember this paradigm here with the 2 planes that look orthogonal to each other, but they are not forming orthogonal subspaces, and because the definition requires that for all V in V and for all W in W, that this equation it is true, and in this case, again, that is not what we have. And again, I mentioned a few times, orthogonality is impossible when the dimensionality of the subspaces V and W, when you add them, you get a number that is higher than the dimensionality of the whole space. Okay, orthogonality is not possible in that case. Okay, finally, we are back to the proving that the null space is orthogonal to the row space. Why is that? One slide, one equation proof basically. If I take AX equal to 0, so X is an element on the null space, I'm going to prove that X is orthogonal to every row. Well, you know, this is row 1, row M, so if I take the AX, the first row, row 1 inner product with X, I get 0. Second row with X inner product is 0. You can immediately see that every row of A is orthogonal to X, which is in the null space. So X is orthogonal to every combination then of the rows. So X is orthogonal to the row space itself. So there it is. The null space is orthogonal to the row space, and both are subspaces of Rn. So this is the easy, nice proof, and this is the way that I want you to remember on how to prove that the null space is orthogonal to the row space. If you try to prove it a little bit differently, you can do that as well. And so let's take X to be a vector in the null space. So let's take a vector from the row space. Remember that A transpose Y, all right, A transpose Y, in the A transpose, the columns have become rows. So A transpose Y, you can actually think of it as a combination of the rows, all right? A product of a matrix with a vector gives you a combination of the columns. Now the rows of A have become columns of A transpose, so A transpose Y gives you combinations of the rows. So literally we need to prove that the inner product of X with A transpose Y equal to 0. So we need to prove that X transpose A transpose Y is equal to 0. And you can write this as AX transpose times Y. Remember, this is X transpose A transpose. And because X is in the null space, this is 0. So there it is. This proof is not the easiest or the one that I want you to remember, but it's also an extremely important way to look this orthogonality, and also to realize that this concept of the transpose of the matrix was just not just an artificial construct to simplify things or do algebra, but it is part of the fundamental theorem of linear algebra, and it is part of the fundamental theorem because it really comes directly in the orthogonality of the null space and the row space of A. Okay, let's do an example. If you take this A and this is a solution 1, 1, minus 1 from the null space, you can immediately see that the first row times this element from the null space gives you 0, so they're orthogonal, and the second row times this vector from the null space also gives you 0. In this case, the null space is this vector alone. It's one-dimensional, so the rows are orthogonal to the null space, as you can see in this example. So the next fundamental theorem we have to prove is that the left null space and the column space are orthogonal subspaces in Rm. And the proof follows similar way, the way we did it for rows. So let me see this directly. So we need to prove that we need to prove that if we take an element from the left null space, so if Y such that A transpose Y equal to 0, then Y has to be orthogonal to the columns. Remember, what is A transpose? You take the columns and you make them rows. So the first row becomes the first column transpose. The last row becomes the nth column transpose. So now immediately you can see the first column times Y is equal to 0. The nth column times Y is equal to 0. So Y is orthogonal to every column of A. It's orthogonal to thus to every combination of the columns of A, and we're effectively done. Okay, so the left null space is orthogonal to the column space of A, and we're completely done with this. And we go back to this wonderful picture again, and you can see that we have the two subspaces of Rn, the row and the null space. They meet at 90 degrees. They don't share any line. They only share the 0 point. They are orthogonal to each other, and most importantly, their dimensions match. And the same thing about the column space and the left null space. They're orthogonal. They meet at the 0 point, and their dimensionalities, they match together. I'm going to come back to explain what is shown in the middle of these pictures in 1 second. Okay, but this is an important part of the fundamental theorem of linear algebra. So, so the key element now that I want to emphasize is orthogonality is one thing, but effectively the two pairs of subspaces that we discussed, they are not just orthogonal, they're actually orthogonal complements. And the question is then, what does orthogonal complement mean? So, right, we discussed this already in terms of dimensions. I told you the null space has dimension n minus r plus r dimensions for the row space. When you put them together, you get dimensionality of equal to n. But this is not really the formal definition of orthogonal complement. So let's see what orthogonal complement is. So definition. If you have a subspace V, the orthogonal complement of V contains every vector that is perpendicular to V. All right? So if you're looking for the space that contains every vector that is perpendicular to a subspace V, that is the orthogonal complement of V, and we write it as V with this nice symbol to indicate orthogonality, V perpendicular if you like. So that is the orthogonal complement of a subspace V. So now with this definition, we can actually comfortably say that the null space is the orthogonal complement of the row space. And, the question is, do we have to do this to prove this again? Let's try to highlight sort of a proof, right? So we need to prove that any vector that is perpendicular to the null space has to be in the row space, and every element that is perpendicular to the row space has to be in the null space. So if you take every x that is perpendicular to the rows, right? Remember how you multiply A times x, right? So every element that's perpendicular to the rows has to satisfy this equation. So it's in the null space, all right? And actually, you can do the opposite. You can do the reverse and say, if you look for every vector that is orthogonal to the null space, that vector has to be in the row space. Because in principle, if you have a vector V that is that's orthogonal to the null space that's not in the row space, you can actually go and add that vector V to the matrix A as an extra row, and that will not affect the null space at all, but it will affect the dimensionality of the row space. It will increase it by 1. But if it increases it by 1, we're going to be in trouble because this nice equation that we have seen, it will not be true anymore. Okay? So if this R increases by 1 and the dimensionality of the null space doesn't change, you will not be able to satisfy this equation. Bottom line, the null space is the orthogonal complement of the row space, and the row space is the orthogonal complement of the null space. And remember, when you put those things together, you basically make the whole of Rn. And similarly, the left null space is the orthogonal complement of the column space, and both of them are subspaces of Rm. So in the first part of the fundamental theorem of linear algebra, we limited ourselves in the dimensionality of the subspaces. Here now we have moved to discussing about orthogonality of the subspaces, and even extremely more important than that, we have discussed the concept that these subspaces in pairs, they're orthogonal complements of each other. If you want to, again, to start thinking what orthogonal complement means is if you take a vector x in Rn, based on the fact that the null space is orthogonal complement of the row space, means that this vector x, an arbitrary vector x in Rn, can be written as a component that is in the row space and a component that is in the null space. This is similarly, having a vector in 2 dimensions and say, I can decompose this in one component in the x direction and one component in the y direction, right? It's because basically the x vector and the y vector are orthogonal complements of each other in R2. So here, any vector x can be written as the sum of the row space component and the null space component xn. So effectively, if you do this and you take the effect of a matrix A on every vector x in Rn, you can see because Ax equal to n, you get Ax becomes Axr. Okay, so immediately see that this row space component of x, this xr, when you multiply it by A, it goes directly in the column space. Okay, somehow we have been able to, through this A, to map the row space to the column space. And the schematic that we had seen before, it was showing an arrow basically indicating this mapping from the row space directly to the column space. And I think we will see this again shortly. So every vector is mapped to the column space. Okay, you remember A times X, what is it? It's a combination of the columns of A. So somehow the only thing we need here is we need the XR component. So effectively what we have is we have a way to move things from the row space to the column space. Okay, from the row space to the column space. So here is something extremely important set here as a theorem. If I take any vector in the column space, this vector comes from a unique vector XR in the row space. So again, if you take a vector in the column space of matrix A, then this B comes from a unique element XR from the row space. So what that means is that AXR is equal to B, and that particular XR is unique. Okay, AXR is equal to B, and that particular XR is unique. The proof is actually simple but still sophisticated, because if you assume that this B comes through 2 different XRs in the row space, then because B is equal to AXR and B is equal to AXR prime, we're going to get this equation. And so the difference XR minus XR prime is going to be in the null space of A. But what is XR? XR is a vector in the row space of A. And what is XR prime is a vector also in the row space of A. So the difference has also to be in the row space of A. So wait a second here. The difference of the 2 XRs is in the row space, but also, as I see here, it's also in the null space. And what is the element that is common to both the row space and the null space? Well, it's the 0 vector, and that's where you see the uniqueness that the 2 vectors basically are identical. So every vector B basically comes through by operating A on a unique element in the row space, and this vector here was denoted as XR. Okay, so effectively we have a mapping from the row space to the column space, and that mapping identifies a unique element XR in the row space. This is extremely important, okay? A unique element XR in the row space. So let's see the big picture here. Here is a B in the column space, and we're trying to solve AX equal to B. In general, any X has two components, XR and XN. If you operate with A on xn, xn is mapped to the zero vector because that's the null space definition. And if you operate AXR, this is mapped uniquely to the vector B in the column space. So effectively, you have a unique map from the row space to the column space. And again, the schematic here, we are trying to solve AX equal to B, where B is a vector in the column space. So we have been able, for any vector B and any matrix A, to identify a unique element XR that maps directly to B. Okay, and again, this decomposition of X to XR and XN, think of it as projecting X to components in the X-axis and the Y-axis. I am doing the same thing here, but I'm taking two components, one in the null space and one in the row space, because they are orthogonal complements of each other. So in solving AX equal to B, basically we're solving AXR equal to B, where there is a unique XR. Now you may say, can you tell us how do we get this point XR and how do we get this point XN? I will give you answers to this when we discuss about projections to subspaces in a follow-up lecture. For now, just conceptually agree with me that you can project X to the row space and to the null space, and remember this geometric interpretation here, that the row space is mapped to B, and for a given B we have a unique element XR. So just a schematic of the null spaces, the null space of A and the row space of A. So the row space of A here is two-dimensional. So that's a plane passing through the origin, and the null space is this line passing through the origin. So effectively, you can see here that this plane and this line are orthogonal complements of each other, and also you can see that there are dimensionalities of 2 and 1 match to give you the dimensionality of the three-dimensional space. All right, so we have come a long way actually to talk about independent vectors and in Rn, and identifying a basis in Rn. So if you have any independent vectors in Rn, they span Rn. If you have n vectors that span, then they have to be independent. Okay. N is related with the basis of this Rn dimensional space, and we have extended this to discussing about the columns and the rows of a matrix A. So if we have n columns that they are independent, and we're talking about square matrices here. So if we have n columns that they are independent, they span Rn, and AX is equal to B is solvable for any B, all right? Because effectively a combination of the columns can generate any vector B, so this has a unique solution. and if the n columns span Rn, then they're independent, okay? Which means that Ax equal to B has one solution. So effectively, these two common sense statements that you see here for invertible matrices have to do with the uniqueness and the existence of solutions of Ax equal B, and I think the next slide sort of summarizes this, that uniqueness implies existence of solution, and existence of solution implies uniqueness. And so let me fast go through this. If the solution is unique for this rectangular matrix in solving Ax equal to B, so if the solution is unique, means you don't have any non-zero elements in the null space, so there are no free variables. So you have n pivot columns, and if you have n pivot columns with back substitution, basically you can solve Ax equal B, so the solution exists. You can go the other way around. If the solution exists, you can show that it's unique, okay? If you can solve this for every B, all right, means that when you did elimination, you do not produce any zero rows. So means all the rows are independent, all the columns are independent, so the null space only has the zero solution. So basically the solution to your Ax equal B is unique. All right, so let me so go back to the orthogonal complement of the subspaces. The row space is orthogonal complement to the null space. So I'm going to make now a major statement that, again, it's very common sense, but in principle needs to be proved, right? So let's say that you have computed the basis for the null space of A, and you have computed the basis for the row space of A. So these two bases have R, dimensionality R, and dimensionality n minus R. So we have R basis vector from the null space and n minus R basis vector from the row space. So take now all of this and form one set of vectors that has total n vectors on it. So R vectors that are basis vectors from the null space and n minus R from the row space. So you know what I'm claiming? That when you put the two bases of the two subspaces together, because they're orthogonal complements, then effectively you have a base for the whole of Rn. All right, this is an amazing result, right? You take the two bases together, you put them together, and you get a space for the whole of Rn. So the proof, again, it's not very complicated, but it requires some thinking. So let's do the following, right? So let's take a linear combination of the basis elements of the row space together with the linear combination of the basis of elements of the null space. So I'm going to take a linear combination of n vectors. Some of these vectors come from the null space, and the rest are coming from the row space, and they're basis vectors of the corresponding spaces. Now, if I do this, will you agree with me that the vectors from the row space, their linear combination will be a vector xr in the row space, and the vectors, the linear combinations from the null space will be a vector xn from the null space, okay? Because linear combinations of the row bases, produce a vector in row space. So I want to prove that the linear combination of all the vectors from the two bases, right, can only give me the zero vector if all the coefficients are equal to 0. So what I have is I have this xr plus xn is equal to 0. All right, xr is a linear combination of the vectors from the row basis, and xn is the linear combination of the vectors from the null space basis. So xr plus xn is equal to 0, and I want to see what combination of the coefficients that are inside xr and xn are actually going to satisfy this equation. So from this equation, we see immediately that xr is equal to minus xn. Now, xr is a vector in the row space, xn is a vector in the null space. You cannot really have two vectors in these two orthogonal subspaces unless these two vectors are the zero vector. Okay, remember from our earlier discussion. So xr has to be equal to xn equal to 0, and we're practically half the way in the proof, because if you look at xr as a linear combination of the basis of the elements from the row space, because those vectors in the base are independent, all the coefficients that they were involved inside the definition of xr have to be 0, and similarly, all the coefficients that they were involved in the definition of xn have to be 0. Effectively, all n coefficients in that linear combination have to be 0. Bottom line, and this is what I want you to remember, if you take the basis for these orthogonal complements from the null space and a basis from the row space, you put them next to each other, they form a base for the space Rn. Okay, this is extremely important for our course. So we don't need to generate new bases from scratch, because basically we have a basis for each of these subspaces. Let me show you an example with this orthogonality and the complements of the row space and the null space. So let's say that you have matrix A that looks like this. And when I look carefully here, I can see the rank of this matrix is equal to 1, right? So there is a null space. Actually, the null space vector is 2n minus 1, right? If you multiply this with 2 minus 1, you get a 0 vector. So let me take an arbitrary vector 4, 3, okay, in R2. So this is a vector 4, 3 in R2. So what I can do is, given this matrix A, I can project this vector and I can write it as a vector in the row space of A, and the row space of A is 1, 2. So actually my xr comes to be 2 times that, the vector 2 and 4, and the vector in the null space that is 2 and minus 1. So actually, if you add those, what do you get? You get 4 and 3. So effectively, you can see this decomposition that any vector in R2, okay, can be written down as a vector in the row space of A and a vector in the null space of A. Exactly, you may wonder on this trivial example, I guess what the answer is going to be. So in a general problem, you may again ask, if you have any vector x in Rn, how do you find its projection in the row space or in the null space? Well, we will see this in the next lecture when we discuss about projection matrices. So I want to finish with something that it will be extremely useful in the next lecture when we discuss about least squared methods, where the matrix A transpose A is going to come to play a role. So I don't want to tell you anything about least squares yet. Just we will see that A transpose A is going to come to play a role, and in some sense, when we did the problem with the graphs application in the first part of the lecture, we noticed there was a matrix that was looking like A transpose A on the left-hand side of our final equation. So the idea is that AX is equal to B is not solvable if we have more equations than unknowns. So in general, you cannot solve that because B doesn't belong to the column space of A. And in that case, we will develop techniques that will allow us to find some solutions. And those techniques require the calculation of A transpose A. And actually, I can give you the least square solutions. It's going to look like this. I'm not going to tell you from where this equation is coming, but effectively we're going to compute an approximation to the solution X that requires to solve A transpose A X hat equal A transpose B. Okay, so effectively we're going to be solving not for X, but some approximation of X, and that is to be defined. And somehow here we have this matrix A transpose A, and someone will ask, and that's what I want to address today, is can I actually with confidence say that A transpose A is invertible? Can I find this X hat? So I want to discuss a little bit about the properties of this metric A transpose A. So if A is M by N, the first property you can immediately see that A transpose A is really a square matrix, is N by N. And also you can see that it's invertible. So it's a very nice matrix. It's square and it's invertible. The question, I'm sorry, it's square and it is symmetric. And the question is it invertible? All right. So here is one example of an A matrix that is 2 by 3. So I have 2 columns in R cube. Obviously, if you take an arbitrary B, it's not going to be in the column space. If you take the A transpose A in this particular case, if you multiply A transpose with A, you get this nice matrix, and you can immediately see actually that this matrix is invertible. So you may ask, what is special about this matrix A that make A transpose A to be invertible? And the answer is because these 2 columns are independent of each other. So in this particular case, all right, the 2 columns are independent of each other, and this is what allows us to compute an A transpose A that is invertible. So in general, the 2 properties for A transpose A that I want you to remember, and we will come back to it, is that the null space of A is the same as the null space of A transpose A, and that the rank of A transpose A is the same as the rank of A. So to be able to invert A transpose A, the null space of A has to be equal to 0, and that's the case in this particular example. So A transpose A is invertible. Okay, so we need to have independent columns, right? And the null space of A has to be containing only the 0 vector. So here's another example. Obviously, the 2 columns are dependent. So if you take A transpose A, you get this nice matrix, and you can see that this matrix is not invertible. Okay, so the null space here is the non, it's one-dimensional. It's actually, you can immediately see the vector -3, 1 is in the null space, and that's what leads to A transpose A not being invertible. So remember that if you want to guarantee that A transpose A is invertible, the null space of A has to be the 0 vector, and all comes from this equation on the top, that the null space of A transpose A is the same as the null space of A. Actually, this equation is obviously trivial, because if you take a vector x, if you take AX equal to 0, and you multiply that with A transpose, you can see that the null space of A transpose A is the same as the null space of A. We're done. So I remind you orthogonality of 2 subspaces. So 2 vectors from the 2 corresponding subspaces have to be orthogonal to each other. So for every vector little v and every vector little w, the inner product has to be 0. We discussed orthogonality of subspaces. So W is orthogonal complement of V when every vector that is orthogonal to V it belongs to W. And we prove, of course, our fundamental theorems that the null space, the orthogonal complement of the raw space, and the left null space is the orthogonal complement of the column space. So not only they're orthogonal to each other, not only the dimensions match, but we have this concept of orthogonal complements, okay, that allows us to take a vector in Rn, for example, and split it in a vector in the row space and a vector in the null space. And obviously, we will take up these concepts in the follow-up lecture. And then if we look at space Rn, there are n independent vectors in Rn, and any n vectors that span Rn, they are independent and form a basis for Rn. So that's all for the lengthy lecture today. The next lecture will involve the concept of projections to subspaces and onto subspaces, and then we will discuss about this extremely practical, very useful in all engineering applications idea of doing least squares and solving, for example, systems with too many equations and too few unknowns, and we will see how we can approximate the solution to these problems with least squares. That's all for today. I'll see you Monday.